just 2 points. Fourthly, I gave you a point and an equation of a line that is parallel to yours. And finally, I gave you a point and the equation of a line that is perpendicular to yours. Anybody got any question on any of those approaches? All right. What we're going to ease into right now is functions specifically. In fact, the title of the section on page 185 is Functions. So we're going to get into the depth of functions themselves today. There's going to be a lot of new terminology and definitions, so you're probably definitely going to want to take some notes. Some of this stuff is going to be a little new. All right. Before we can talk about functions, we need to talk about something called relations, because relation is, in fact, a broader category of which functions is a subset. So here's our first definition of a relation. As you can probably tell by the definition, there's nothing specifically mathematical about this definition. It's just a relationship between things in one set, what we call elements, and things in another set. We haven't talked about this yet, have we? Good. Hey, every time you go to the grocery store, you see a relation. You see a working relation. Consider these two sets. Every time you go to Kroger, you get a bunch of items on the shelves, right? Unless it's right before a hurricane, in which case there's nothing. But typically you go to the store and there's a bunch of items. And what you discover is that every item is related to a price. If it wasn't the case, you'd go much more often. But every item is related to a price. And some of them are related to the same price, right? That's an example of a relation. Hey, here's another example of a relation, especially as we move into the political season. Every state has U.S. senators. Texas has how many senators? 2. Texas has 2 senators. West Virginia has 2 senators. New York has 2 senators. Etc. All right? So every state is related to 2 senators. So those are examples of relations. And as soon as you start picturing this and talking about the first set and the second set, we can get more specific by naming those first and second sets. The first set is called the, anybody got a notion? First set's the domain. Thank you very much. This is the domain. That's the set of first elements. And I bet more of you now know what the second set is.
Range.
It's a range, absolutely. So I will be talking about elements in the domain, or domain elements, or range elements. So it's nice to know what those are. Okay. Just some terminology. Now, we're not going to deal specifically with relations. We're going to deal specifically with a subset, a narrowing definition that we're going to call functions. So, every function is a relation, but every relation is not a function, which we will see in just a second. Here's my second major definition. Notice that every function is a relation, but it's a relation in which, in other words, a very specific kind of relation. The in which describes what makes this relation a special relation that we're going to call a function. It says a function is a relation in which every element in the first set, the domain, is mapped to only one element in the second set, the range. So let's look at these first two relations and see if either one of them is a function. Question: is every item mapped to a price, a single price?
No.
Yeah. A is just mapped to one thing, right? B is just mapped to one thing. C is just mapped to one thing. And that makes perfect sense. And it'd be very frustrating if you went to the checkout counter and had to pay, a certain price on odd hours and a certain price on even hours. So, hey, everything is related to one price. Now notice, all I have to consider to see if this guy is a function is the first set. All I have to do is say, is every first element mapped to just one thing? And as long as there's just one line leaving every first element, I got myself a function. How about this second relation? Is that a function? Got some problems, right? In fact, every single state is a problem when it comes to the definition of a function. Texas has two lines of relationship. Two senators are related to Texas. West Virginia, two lines of relationship. Not a function. So this guy is a function. This guy, however, is not. Now, there's no limit as to how many elements can be related to how many elements in the range, for instance. Is that a function? Yes. It is. It's a strange-looking function. In fact, it's called a many-to-one function. Everything is matched or related to just one thing, but it's a function. And all I have to do is go, yeah, I see now. Every element is mapped to just one thing. All right. Let's look at a specific relation, see if this guy is also a function. And we'll kind of relate it to mathematics. You'll probably see how I start with my first elements and get my second elements. First of all, is that a function?
Yes.
It absolutely is. Can you tell what I'm doing? Squaring. You're squaring. And in fact, this is an example of, or a little part of, the squaring function, in which I take a value from my domain, square it, and I get values in the range. Typically, when we talk about functions, we use middle letters, like f of x. That's how we talk about functions. We use the middle letters of the alphabet. F of x, h, k. Those letters are letters that typically show up in function notation. All right. So you can recognize if a relation is a function if it's in a mapping like this. But I got some bad news. Most functions do not show up as a mapping. More frequently, they show up as ordered pairs. Like ordered pairs of numbers. Can you give me an ordered pair that comes from this function, f of x right here? 1, 1. Absolutely. 1 is related to 1. Give me another one. You got it. 2, 4. So you see that this is another way of listing the first elements by listing them first in ordered pairs. And just as I could ask you from the mapping, what are the elements of the domain? You tell me 1, 2, 3, 4. Likewise, you can look at the ordered pairs, and I can say, what are the elements in the domain? And you go 1, 2, 3, 4. Now, if I got a mapping, I can look at it and tell if the thing is a function. Every first element mapped to just one thing, got myself a function. But let's assume I just have the ordered pairs. I no longer have that mapping to consider. So I need another question I can ask myself. And it's this. Is any first element repeated? Is any first element repeated?
No.
If the answer is no, I got myself a function. So that's the question to ask yourself of ordered pairs. Is any first element repeated? The answer is no, I got myself a function. If G, I said no. Obviously. So what I'm looking for is no first element repeated. If that's the case, got myself a function. All right. Bad news still. Most functions do not show up as ordered pairs. Or if they do, they show up as an infinite number of ordered pairs. Now, I don't know about you, but I do not have time to list an infinite number of ordered pairs and check and see if every first element is unique. I don't have time. I got better things to do. All right? So we have another way of indicating an infinite number of ordered pairs. You probably know what that is. It's a graph. Here's an infinite number of ordered pairs. In fact, it is part of that, or it is the fullness of that relation we were looking at right here. This is the squaring function. This is y equals x squared. Or to put it another way, f of x equals x squared. There's an infinite number of ordered pairs there. Every point on that parabola represents an ordered pair of numbers. I don't have time to determine if there is a first element repeated. So I have another test when I have a graph. Anybody know what it is? I heard somebody say. Yes, the vertical line test. The vertical line test is the one that determines if this guy is a function or not. Here's what you do. You ask yourself the question, is there any vertical line, and you've got to use your imagination, is there any vertical line that is going to cut this graph in more places than one? Is there? No. Every vertical line will cut that graph in exactly one place, right? So, since there is no vertical line that cuts this graph in more places than one, we say it passes the vertical line test. If it passes the vertical line test, you got yourself a function. So look at what power you have, ladies and gentlemen. You can evaluate an infinite number of ordered pairs. You just did. You can evaluate an infinite number of ordered pairs with a simple, physical, what we call the vertical line test. It revealed, by your observation, that no vertical line is going to cut this guy in more places than one. Therefore, it is a function. Let me ask you a question. True or false? I like this. True or false? Every upward or downward turning parabola represents a function. True. How do you know it's true? Because they pass the vertical line test. Every upward or downward turning parabola passes the vertical line test, therefore is a function. Remember these 4 kinds of slopes you looked at last time we were together?